So, after having defined the axioms of probability and I tried to show you how probability function can be obtained, let me now derive a few propositions using these axioms. So, the topic that I am going to talk about is simple propositions. So, proving this property that proposition that p phi is 0. So, in axiom 3 we take E1 to be omega, and then EIs are all remaining EIs are empty, and here we will take the index set to be a finite index set. So, it does not matter, I have to prove it I have to just show that p phi is 0. So, whether I take so here it is convenient to take I to be a finite index set. So, I take I to be a finite index set, then all other EIs are empty sets. So, therefore, the condition for axiom 3 is satisfied, because certainly E1 is disjoint with an empty set, and all other sets are also, because they are all empty. So, they are disjoint. So, therefore, I write down applying the axiom 3, I say that p omega plus p of phi, and phi gets added I minus 1 times, because 1 has gone here. So, 1 less than the index of I, cardinality of I. So, therefore, this is p phi into cardinality of I minus 1. This has to be equal to 1, because this is p omega, right. Since you add up all the EIs, then they all add up to omega. The remaining sets are all empty sets. So, this is by axiom 2, this is 1, right. And so, therefore, since I is a finite number which is greater than or equal to 2, because we are saying that there is at least one set which is equal to omega, and the other there is at least one set which is the empty set. So, therefore, the number of the cardinality of I has to be 2 or more than 2, and so this number is not 0. Therefore, here you see, because p omega cancels out, then you get that also p omega is 1. So, anyway, this cancels out and you are left with this equal to 0, which means that either this is 0 or this is 0, but then this number is not 0, since cardinality of I is 2 or more than 2. So, p phi must be 0. So, this is how we obtain the proposition that p phi will always be 0. Now, proposition 2 is this actually, that probability of the complement of event E is 1 minus probability of the event E, and this can be very simply derived. And see, here the attempt is to show you that once you define the axioms, and then using the axioms logically, you can derive at so many results and build up a good structure. So, that then you can estimate probabilities of more complex events and so on. Okay. So, now for any event E union E complement is omega, right, either a element of omega is in E or is in E complement. So, this holds. Then since E and E complement are disjoint sets, they are mutually exclusive. From axiom 2 and 3 it follows that P E plus P E C is 1. So, from axiom 3 it says that probability of E union E complement is P E plus probability of E complement, and then axiom 2 says that probability of omega is 1. So, this is what holds, and therefore, from here it immediately follows that probability of E complement is 1 minus P E. So, that is your second proposition. So, therefore, now using the basic 3 axioms, I have been able to arrive at the result that p phi is 0, and then now I have shown you that p of the probability of the complement of an event is 1 minus the probability of that event. Proposition 2.3 says that now, and you can see that the results are getting more and more complex. So, if there are 2 events E and F subsets of omega, then probability E union F is equal to probability E plus probability F minus probability in intersection F. Okay. And you see that in case E intersection F is empty, then this will be 0, because we have just derived the result that p phi is 0. So, in that case P union F would be this, and this again is valid from axiom 3, because in case E intersection F is empty, then E and F are disjoint, and then we said that probability of the union is the sum of the probability, right. So, this is in compliance with your axioms and so on. Now, let us start proving this result. So, I will first say that E union F is E union E complement intersection F, right, because this set E union F. So, either whatever the elements of F are in E, that gets covered here, and the remaining elements of F are not in E. So, they are in E complement, and therefore, you can write E union F as E union E complement intersection F. Now, by doing this, you see I have broken up this union into the union of two disjoint sets, because E and intersection with E complement intersection F is empty. See, there can not be any element which is in both E and E complement. So, therefore, this is empty. And so, now axiom 3 again says, because these two sets are disjoint, therefore, probability of this union. So, probability of E union F is equal to probability E plus probability E complement intersection F, because I could decompose this union into the union of two disjoint sets. And so, I can immediately apply axiom 3 and I get this, right. Now, we will try to write again decompose F in a way, so that I can make use of the axiom 3. So, now F is F intersection omega, but then omega, as we said, we can write as E union E complement. I just used it here. So, then F intersection of E union E complement, which I can write as F intersection E union F intersection E complement. This is by the distributive law, which I defined some time ago for you. So, therefore, in the earlier lecture. So, therefore, this is equal to this. Now, here again you see that these two sets are, or okay, it should be union. You have to be careful, because there is no meaning of putting a plus sign here, these are subsets. Fine. So, this is equal to this. Now, here again both the sets are disjoint. So, therefore, when I write probability F, I can simply write it as probability E intersection F plus probability E complement intersection F by using our axiom 3. Now, from here, from this relationship, I can now compute probability E complement intersection F as equal to probability F minus probability E intersection F, right, and this I will then substitute in 1. So, I will get P E plus P F minus probability P intersection F. So, substituting this in 1, we obtain the desired result, that probability for any two sets, probability of the union of those two sets is sum of the probabilities of the two sets minus the probability of the intersection of the two sets. And there is a very intuitive argument for this, for the validity of this result. Now, since you see E intersection F is a subset of E and F both, right. E intersection F, these are the common elements. So, they occur in E as well as in F, and therefore, when you are adding up the probabilities P E plus P F, probability of E intersection F gets added twice. So, I have to subtract it once to make the equation balanced, and therefore, this is the result, right. And even through Venn diagram, you can explain that when you see this is A, this is B. So, probability A is this area, probability B is this whole area. When you put them together, you have added this area twice, yeah, because this is your A intersection B. You have added this area twice, and therefore, you need to subtract it once, so that the two equations are balanced. Okay. So, immediate corollary of this result, that P E union F is P E plus P F minus P E intersection F, is that if A is a subset of E, then the probability of A is less than or equal to probability of E. Now, we can write E as, because A is a subset of E, therefore, I can write E as the subset E, I mean the set E I can write as A union A complement intersection E, right, because if this is E and this is subset of A. So, then this is A and this portion is your A complement intersection E, right. Okay. So, therefore, and then these two will be disjoint sets. So, therefore, P E will be P A plus P A complement intersection E, again we are applying axiom 3, because the I have decomposed the event E into sum of two disjoint sets, two disjoint events, and therefore, the probability of P E would be P A plus P A complement intersection E. And since P of A complement intersection E is greater than or equal to 0, therefore, this implies that from here that your P E is greater than or equal to P A. So, an immediate consequence, and I have just put it down, so that for completeness sake, otherwise one can immediately once you have proved this result, you can conclude this result immediately. So, once you have these three propositions, now you can see, you can get some more results, you can compute probabilities of more interesting and complex events. So, consider this example. This says that 20% of Indians smoke cigarettes, 40% smoke BDs, and 7% smoke both cigarettes and BDs. Okay. So, what percentage of people do not smoke both? So, you are asking what percentage of people do not smoke cigarette as well as BD. So, now here if I write the event E as a set of people who smoke cigarettes, and F is my set of people who smoke BDs, right. Then I will first compute E union F. So, probability of E union F by the proposition that I have just proved is P E plus P F minus P E intersection F, right, which adds up to 0.2 plus 0.4. See, this is 20%, 40% and then minus 0.07. So, therefore, this comes out to be 0.53, and I am looking for the what percentage of people do not smoke both. If this is E union F, right. So, E union F, remember when I was talking of De Morgan's laws, this complement was E complement intersection F complement, right. So, this is people who do not smoke cigarettes, people who do not smoke BDs. So, the intersection will give me the set of people who do not smoke either cigarette or BD, right. So, therefore, I am computing E union F complement. Now, here I have used proposition 2, I think 2.2, where I have computed probability of E union F. So, now I want to compute probability of E union F complement, which is 1 minus probability E union F, and say therefore, this is 1 minus 0.53, which is 0.47. See, we have already you have come across notion of continuity of a function on the real line. Now, we want to introduce this concept of probability function as a continuous set function, and this is very useful, because often when we have to take limits of sequences of a sequence of events, and then we need to have this notion of probability as a continuous function on the sets, so that I can interchange the limit and the process of taking the limit and the probability and taking the probability. So, this is what we are going to formalize. Sequence of events E n and greater than or equal to 1 is said to be an increasing sequence if E 1 is contained in E 2, contained in E n, and so on. So, this is right. Okay. So, this is the notion of increasing sequence of events, and then similarly a decreasing sequence would be when E 1 contains E 2 contains E n, and so on. For an increasing sequence E n, we define the limit of E n going to infinity as union I varying from 1 to infinity E I, right, because anyway it is an increasing sequence. So, this in fact is E n, and therefore, there is nothing new in the definition, because these subsets are all events are part of E n. So, therefore, union actually is, but we are right, because we want to take the concept of interchanging the probability and the limit. So, this is why we are doing it. For decreasing sequence E n, we define the limit of E n as intersection I varying from 1 to infinity of E I. Okay. Now, the proposition is that if E n is either increasing or decreasing sequence of events, then limit P E n. So, here this is the main result, that limit probability E n as n goes to infinity is probability limit of E n as n goes to infinity. So, what we are saying is that you can interchange the operation of taking the limit and taking the probability, because of continuity of P on the set on the sets. So, let us just quickly look at the proof. Consider the case when E n is an increasing sequence, and then we can also go over the proof when E n is a decreasing sequence. So, define new set of events f I as follows: f 1 is E 1, then f 2 is E 2 intersection E 1 complement. So, therefore, you see whatever common components of E 1 were there in E 2, they are not there anymore in f 2. So, f 1 and f 2, f 1 is E 1, f 2 is E 2 intersection E 1 complement. So, therefore, you can immediately see that f 1 and f 2 are disjoint. Right. And then finally, this way you go on, define f n as E n intersection or union I varying from 1 to n minus 1 E I complement. So, all the previous sets E i's, you take the union and take its complement, then you take the intersection with the E n. So, that is B f n. So, therefore, you can see the way systematically the way we have defined f 1, f 2, f n and so on, that these are all disjoint subsets or disjoint events, right. And yeah, so that is what we are saying, that f I greater than or equal to 1 are disjoint. Now, union I varying from 1 to n f I is union E I, right, because I am not taking away anything, it is only just the common parts I am removing, and so making these disjoint, but otherwise all the elements of all the components of E 1, E 2, E n are all there. So, union f I varying from 1 to n is union I varying from 1 to n E I, and therefore, in the limiting case also this will be true, right. Now, probability union E I varying from 1 to infinity is probability this, because this holds. So, therefore, this is also probability union I varying from 1 to infinity f I, and since f i's are disjoint, I can write this as summation I varying from 1 to infinity P f I. Since f i's are disjoint, right. So, I can write this, and now on this side you see this is nothing but limit E n by our definition, right. We define that union E I varying from 1 to infinity is limit E n goes to infinity. So, this is this, and from this side you see this is sigma P f I varying from 1 to infinity, which can be written as limit n going to infinity of summation I varying from 1 to n P f I, which again here this you will write as union I varying from 1 to n f I, and then this will be limit. So, this is E n, right. Yeah, this part is also okay, union f I, yes, you can see it immediately that union f I is E n, because E n is an increasing sequence, and therefore, this is this. So, now this is what you wanted to show, right. Probability limit E n goes to infinity is equal to limit probability E n as n goes to infinity for an increasing sequence. Now, when the sequence is decreasing, then you see E n complements will be increasing, right, because E n's are decreasing. So, E n complements would be increasing, and so you apply what we have just proved to this sequence of events E n C, and so probability union I varying from 1 to infinity E I complement is limit probability E n complement and going to infinity, right. But this union is nothing but intersection of E I varying from 1 to infinity complement, right, by your De Morgan's laws that we had done in lecture 2 or lecture 1, I think in the previous lecture. So, then this is this, therefore, intersection E I this thing from here. So, now this is, because this is equal to this, remember, because we have taken these as increasing, these are increasing sequence. So, this is equal to this. So, it follows from here that this is equal to this, right, by our this thing, and this you can write as 1 minus probability intersection E I varying from 1 to infinity, because this is complement probability of the complement event. So, 1 minus probability intersection I varying from 1 to infinity E I, and this is same thing, you are writing probability of E n complement. So, this will be 1 minus P E n. So, this comes to this side, and here you have this, and this, because this cancels out 1 1, and therefore, this now is by your definition because it is a decreasing sequence. So, by definition I varying from 1 to infinity E I, this is limit E n as n goes to infinity. So, therefore, you have proved the result for both, right. And now, there will be many occasions where we will be using and I will be referring to, because P is a continuous function, continuous set function. Therefore, I would be very often exchanging the process of taking the limit and the probability. So, now I will define another new concept, which is the conditional probability, and we will just see that how starting from the 3 axioms I am able to develop more and more theory about the probability. So, conditional probability, again I will take an example first. So, suppose you have 2 fair dice, the unbiased dice we can also call fair, all these words are synonymous. So, when you have when the example we had considered of rolling or tossing 2 dice, then if my event A is that the first die shows 2 and B is the event that sum of the numbers on the 2 faces is they add up to 6, right. So, but the first die is already showing a number 2. Now, the conditional probability, that means knowing that the first die has shown a 2, then if I want the sum of the 2 numbers on the 2 faces to be 6, and now we want to find the conditional probability of B given A. So, therefore, see what will be B intersection A? That means, if the first die is showing 2 and then you want the sum of the 2 numbers to be 6. So, that means the other die must show the number 4. So, this gives you the intersection of A and B, 2, 4, right. And here, given that your first die, so the probability that the first die has shown 2, then the second die can show any of the 6 numbers, and therefore, the probability of A, because this probability is B, probability of B intersection A divided by probability A. So, probability A will be that first die is showing a number 2 and the second die is showing any of the 6 numbers. So, therefore, this add up to here this. So, now the probability of 2, 4, just one of the 36 equally likely elements, because we are assuming that the die is unbiased, it is a fair die, both the die are fair. So, the probability of this pair occurring is 1 by 36, right, and each of this is again equally likely, and so each of them has probability 1 by 36. So, that will be 6 upon 36, which will be 1 by 6, and therefore, the outcome is 1 by 6. Okay. So, this is how we compute the conditional probability, and so we say that B, the probability of B given A is the conditional probability of B given that A has occurred. So, once you know that this event has taken place, now you are wanting to find out the probability that B will occur. So, therefore, this is the conditional probability of B given A. That means, you want to compute the probability of B once you know that a certain event A has already occurred. Now, so a formal definition would be that if P A is positive, that means A is an event which actually can occur. Then, if probability P A is greater than 0, we say that probability B condition A is equal to probability of A intersection B divided by probability A. So, this is the definition, and this is a valid one, because we have already assumed that P A is positive. Okay. So, here you can immediately say that this implies that probability, you can also write another way of writing probability A intersection B is probability A into probability B condition A. So, this is a very important formula which we keep using very often, and so let me illustrate this concept through this through an example. Now, in the game of bridge, 52 cards are dealt and are equal to the 4 players. That means, each player gets 13 cards, and so the 4 players are A, B, C and D. A and C have both been dealt 7 clubs amongst them. Okay. What is the probability that B will have 4 clubs? This is the question. So, now the event that has already occurred is that A and C both together have 7 clubs amongst them. Now, we want to find out the probability that B will get 4 clubs, right. So, here again I am using multinomial coefficients, and I am saying that the number of ways in which 4 clubs out of, see, because they have been dealt 7 clubs amongst them, a number of ways in which 4 clubs out of remaining 6, this should be 6, sorry, this should be 6, because 7 clubs have been dealt to A and C. So, you are left with 6 more clubs, and therefore, this will also be number 6. So, now you want 4 of the out of the remaining 6 clubs, you want 4 of them to go to player C, player B, right. And so, if he gets 4 clubs, then that means since he is getting 13 cards, so after the remaining 19, so this will be then 20, sorry, 20. So, from the remaining 20, he should get 9, right. So, I have to correct the thing here also, this is 6 and this is 20. Okay. So, I have made the, I have computed this probability by using the multinomial coefficients, that there are 2 sets of cards, and so the choice is from 6, 4 out of 6 and 9 out of 20, and the total ways in which he can be dealt 13 cards out of the 26 cards, because 26 have already been given to A and C. So, out of the remaining 26 he has to get. So, total number of ways which in which that can happen is 26, choose 13, and this is this. Now, you have to explain this in terms of, so I am saying that the conditional probability of B getting 4 clubs when A and C have already been given 7 clubs is given by that number, and then I would like you to now, because yeah, okay. So, just figure it out how this will fit into this definition, and I will come back and then discuss with you again if you have figured it out as to how this fits into that definition. Okay. Now, let me give you another extension of this concept of conditional probability, and then so just want to point out here that Bayes is a name. So, therefore, the apostrophe will will be put after S. Bayes is the name of the statistician, and so Bayes formula, which we will, as we go on, we will show that it is a very useful way of computing certain probabilities, conditional probabilities of course, and so we will continue with telling you what the formula is, and then taking some examples to illustrate how it is used. So, suppose E and F are 2 events, then as already shown to you, I can write E as E intersection F union E intersection F complement, right, since F and F complement are disjoint, and also E intersection F and E intersection F complement are disjoint. Okay. And therefore, immediately we had concluded that P E can be written as P E intersection F plus P E intersection F complement. Okay. Now, we can generalize this formula, because if I have n mutually disjoint of E intersection F I, right. If you remember this, then that means I am giving you a formula for computing probability of E by conditioning E on the F I's. So, if I have a set of these mutually exclusive F I's such that they add up to their union is equal to my whole sample space omega, then I can decompose P E in this way, and then using the conditional probability formula for E intersection F I, I can write this as this, and now this is a way of computing P E by conditioning E on the occurrence of F I's, right, into F I. Right. Or in other words, you can also look upon this as a, because your P F I's summation this will be equal to 1, remember, because this is equal to this, they are disjoint. So, probability of union F I's will be sum of the probabilities of P F I's, I mean, and therefore, that will be equal to 1. So, this is equal to 1. So, I can treat probability F I's as weights, and therefore, this formula is saying that P E is the weighted average of probabilities E condition F I by the weights P F I, right. So, whatever conditioning event you take here, you multiply it by the corresponding weight, and this. So, there are many ways of looking at this, right. Now, why I am discussing this is because now suppose that E has occurred. Suppose now that E has occurred, then you want to find out the probability of occurrence of F I. See, I have changed the role of the two events, saying that suppose E earlier I was computing E given dependent conditional on the occurrence of the events F I's. Now, I am saying that if I already know that E has occurred, then what can be the probability of the occurrence of a particular F I, because see, the thing is that F I intersection F j is empty and union F I is omega. So, therefore, only one of the events can occur here exactly, because they are mutually exclusive. So, two events cannot occur at the same time. So, this has occurred. So, in that case what we are saying is that when E has occurred, I want to compute the probability of F I occurring, right. So, that means I want to compute the probability F I given E, that given that E has occurred. So, again using this formula that I just obtained, this will be P F I intersection E divided by this, okay, because probability E I have just computed for you is given by this, right, and this is F I intersection E by my definition of the conditional probability. So, this is this, right. Now, P F I given E is the posterior probability of F I when E has occurred. So, I am going to call this as the posterior probability of F I given that E has occurred. And so, I will now take up an example to show you what we mean by this. So, I will give you now an example of computing the Bayes probability. And here I am considering this example, and even in some other previous examples in the other lectures, I have mentioned SR, which means that I am taking these examples from the book by Sheldon Ross, and I will give you a proper there are two books by Sheldon Ross, which both I have referred to while preparing these lectures. So, I will give you the proper references at the end of the this section. Okay. So, now let us understand this problem very well. There is an insurance company. It divides its clients into two classes. See, there is somehow there is this information that a set of people are more accident prone than some others. There is some ways of computing this, and so maybe because of the past history or something, if somebody has had lot of accidents and somebody has not had, then because the insurance companies, they depend on this kind of data. So, let us say that class 1 is the set of people who are accident prone, and class 2 is the set of people who are non accident prone. That means, they have had very few accidents in the past. Right. Now, in a period of fixed 1 year, so the whole thing that we are looking at is during a given period of 1 year, fixed period, the probability of accident prone, the probability of accidents for class 1 of people is 0.4. Okay. That means, the probability of an accident prone having an accident is 0.4, and the probability of a non-accident prone person having an accident is 0.2 in that fixed period of time that you have set, right. And it is also known that 30% of the population is accident prone. That means, the number of people being in set 1, that probability is 0.3. Okay. Now, suppose the event that we are looking at is that a new policy holder will have an accident within a year of purchase of the policy. So, there is a person who has just bought a policy, insurance policy, and now you want to compute the probability that this person will have an accident within the year, okay, within the year of purchase of the policy. So, I will again using this decomposition principle, I will say that probability E can be written as probability E condition on I into probability I plus probability E condition on 2. So, that means, this is non-accident prone and this is non-accident prone. So, probability E condition on 2 and then into probability 2. That means, the people having accident, right. When I am say P 2, I mean that probability of a person who is non-accident prone having an accident, and here this is the probability that an accident prone person has an accident. and I have those probabilities, right. I have this probability. So, the whole thing is accident for a set of people in say I, which I am writing in short form as P I, and for this I am writing P 2. Okay. So, this we can easily compute, because this conditional probability is given to me, which is 0.4, right. Given that the person policy holder is accident prone, he has an accident, that probability is 0.4, and the probability that the person is accident prone is 0.3. So, therefore, this number is 0.4 into 0.3 plus the probability that the person policy holder has an accident when he is non-accident prone, that probability is given to me to be 0.2, and then the probability that he is non-accident prone is 0.7, right. So, when you compute this number, this comes out to be 0.26. That means, a new policy holder having an accident within a year of purchase of the policy is 0.26. Now, I want to compute this conditional probability I given E. That means, an accident. So, when you look at the intersection, so this will actually be by our definition I intersection E divided by P E, right, which means that, see, if you just read this, this intersection of two events says that a new policy holder, or that means a person who has purchased a policy currently and is accident prone, will have an accident within a year of purchase of the policy, right. If you read carefully the event I intersection E, E simply says that a new policy holder, that means a person who has just purchased a policy, will have an accident within a year. I says that the person is accident prone. So, therefore, the intersection will be that an accident prone person, policy holder, will have an accident within a year of purchase of the policy. So, that is this, and this is divided by P E, right. Now, what I will do is, because, so I given E condition E I do not have, but I have this probability. So, therefore, using this definition of, remember I gave you the alternate definition of intersection of the set. So, this is P I intersection E, I can write this as P E given I, that means accident prone, and then the person is having an accident within a year into P I divided by P E. P E I have already computed as 0.26, and so here this is 0.4 into 0.3, this I already know, right, remember from here the first part, and so this is, so now this goes up to 0.4615. So, earlier probability for accident prone, right, earlier probability for an accident prone person to have an accident was for earlier probability for accident for I was, sorry, this is 0.4, right. Probability of accident for an accident prone was 0.4, but now the posterior probability, that means after knowing that the person has had an accident, remember I am computing now, the policy holder has had an accident and he is, so the probability of the accident prone person having an accident, knowing that he has had an accident, has now gone up to 0.4615. So, the posterior probability of accident for the accident prone has gone up from 0.4 to 0.4615. So, actually this is a little complex concept, and I will keep coming back to it through examples to make sure that you you sort of get a better feeling for the Bayes computation of Bayes probability. Okay. Now, the moment you define conditional probability, you then come to the concept of independent events. So, let me just motivate the reason for motivate this definition. And so, here you see what is being said is that if this conditional probability of E given that f has occurred is equal to P E, that means that the occurrence of f has no effect on the occurrence of E, right, because this probability has remained unchanged even though I know that event f has occurred. So, these are the kind of things, because you want to know what kind of events can have effect on the occurrence of some events and so on. So, this is also a very important concept, and you need to know how to compute it. And so, therefore, if this is so, then you see by definition of the conditional probability of E given f is P E intersection f divided by P f, but then we are saying that this is equal to E, probability of E, right. That means, I am just trying to formalize this concept, that if occurrence of an event is not dependent in some sense on the occurrence of another event, then we would be defining this concept of two events being independent. And so, this is essentially this is what you will say, that if this is equal to this, then occurrence of f has no effect on the occurrence of E. And now, by our definition of conditional probability, I will write it as this, but since this is equal to P E, this implies that probability of E intersection f is P E into P f. And so, this is our concept of two events being independent. And so, I will just write down the definition 2.9, which says that two events E and f are said to be independent if P of E intersection f, that means probability of E intersection f, is equal to P E into P f, right. So, let us look at this example. A card is selected from an ordinary pack of 52 playing cards. Okay. Now, E is the event that selected card is a king, fine, and then f is the event that the card is a club. Then you can immediately show that the events E and f are independent, which you can also argue intuitively also, that a king need not be a club and so on. So, let us now show that this gets validated by the definition also. See, to compute the probability of E that the selected card is a king. So, since there are 4 kings in the pack, so therefore, the probability of P E is 4 by 52, and selected card is a club. So, 13 cards belong to the club. So, therefore, the probability of f will be 13 by 52, and P of E intersection f is probability king of club. So, that is only one card, and therefore, probability of that is 1 by 52. So, therefore, P of E intersection f is P E into P f, which is 4, 13 by 52 is 1 by 4, and so 4 into 4 gets cancelled, and so P E into P f is also 1 by 52. So, the two probabilities are equal, and therefore, E and f are independent. Now, similarly, if you look at this other example, 2 fair dice are rolled, and if E 1 is the sum of 2 numbers, is the event that the sum of 2 numbers is 5, right, and f is the event that the first die shows 3. Then you see E 1 intersection f will simply be the event 3 comma 2, that means I must have the pair 3 comma 2, then only, because I know that this is already 3. So, then this number must be 2 in order for the sum to be 5. So, this again probability is 1 by 36, but P E 1 is what? That means, E 1 is the sum of the two numbers being 5, this is 2 3, 3 2, 1 4 and 4 1. So, these are the 4 possible pairs which will give me the sum as 5, and so this probability will be 4 by 36, right, each being equally likely, and the first face showing you 3 is 1 by 6, because here again each face is equally likely, each number is equally likely. So, then this probability, the probability of E intersection f is not equal to P E into P f. So, we will say that E and f are not independent events. Now, consider the event E, which is the sum of 2 faces is 7, right. So, if I change the event from E 1 to E, which requires that the sum of numbers on the 2 faces is 7, then you can see that these are the pairs which are valid for this event, and therefore, they are 6 in number. So, probability E will be 6 upon 36, which is 1 by 6, and probability f already we have seen, which says that the first die must show number 3. So, that probability is again 1 by 6, and so now you see that if you look at the event E intersection F, since F says that the first die has to show the number 3. So, then for the sum to be 7, the second die has to show the number 4. So, this is the only possible element of omega which is favorable to E intersection F. Therefore, here the probability of E intersection F is 1 upon 36, which is equal to P E into P F. So, therefore, you can see how one can define events which given the event F, for example, what are the events which are independent of F and which are not. In the earlier case, when we took the event E 1 to be the event that the sum of the two faces is 5, then you saw that E and F were E 1 and F were not independent, but if I take the sum to be 7, then it turns out that the two events are independent. And now, if you try to define another event E 2 say, which says that the sum of the two faces is 8, then again you can show that F and E 2 will not be independent. So, you should now play around and get a feeling for the definition by constructing different take the same experiment, that is throwing up of two dice, and then try to construct a set of events which are independent, which are not, and so on. So, you can get a better feeling. Now, continuing with the again, as you see, we define a concept, then using the axioms we come up with new propositions, and you see the theory keeps developing. So, if two events are independent, then you will say that E and F complement are also independent. That is very intuitive and you should be able to rationalize it, but in any case we will prove it analytically also. So, the proof is simple. If E and F are independent, then by definition probability of E intersection F is P E into P F, and since we have already seen that you can write P E as probability of E intersection F plus probability of E intersection F complement. So, then we want to compute this. So, this will be from here probability of E intersection F complement will be P E minus from here P intersection F, but then because E and F are independent. So, P intersection F I can write as P E into P F, and so you see this comes out to be P E multiplied by 1 minus P F. I can take P E common outside, and 1 minus P F is F probability of F complement, and therefore, probability of E intersection F complement has been shown to be equal to P E into P F complement, and therefore, by our definition E and F complement are also independent, and which says that if occurrence of F has no effect on the occurrence of P, and when I say occurrence, that means the probability we are talking of. So, E and F being independent says that occurrence of F has no effect on the occurrence of E. Therefore, occurrence of non-occurrence of F should also not have an effect on E. So, that is what we have concluded, that if E and F are independent, then E and F complement are also independent. Then now here I am again just making a statement, and I want you to construct examples for yourself. So, what we are saying is that if suppose E and F are independent and E and G are independent, then E may not be independent of F intersection G. Now, this may not sound very intuitive, okay, but it can be, you can construct sets E, F and G to show this, right. So, that means now I have already told you to explain this the example that I took earlier, and now I want you to also construct sets E, F and G, construct an experiment and then construct the corresponding events E, F and G to show that if E and F are independent and E and G are independent, then E may not be independent of F intersection G. And in fact, you can remember the throwing of two dice that I have taken that experiment, and there also you can construct sets E, F and G to show that this is valid, this statement is valid. But then I can come back and discuss some examples with you. Fine. Now, if you want to extend the concept of independence of two events to more than two, then I will just show you how things start becoming difficult, even if you just take the want to extend the concept to three sets. That means, if three events E, F and G are independent, then we require that not only should the probability of intersection of E with F with G and intersection with G should be equal to the product of the individual probabilities, but when you take two at a time, these three sets from these three sets, then P of E intersection, that means the any two subsets here should also be independent. It is not just that the product of the that is the probability of the intersection of the three sets is equal to the product of the individual probabilities, but when you take two at a time, then also that should be the condition of independence should be satisfied. So, all four conditions have to be met before you can say that the three sets E, F and G are independent. So, now here again we need to construct, and you can immediately see that the moment you increase the number of sets and you want to talk about their independence, then this will get more complex and the number of conditions will go on becoming larger and larger. So, therefore, I will just leave it at this point for this thing, and then one can always look up advanced textbooks where they will give you conditions for any set independence of for any set of for any number of subsets or events, right. Now, here again an interesting way to try to understand this concept would be to construct subsets E, F and G, which may satisfy not all the conditions, but only some, to show that all four conditions are necessary for independence of the three events E, F and G. Right. So, I will now take up a set of exercises 2, and then we will come back to constructing examples for these situations.